Hello, my name is Ron Satz. I'm president of Transpower Corporation, a systems engineering and consulting company founded in 1976. I hold a Bachelor of Science degree in Engineering Science and a Master of Engineering degree in Transportation Engineering from the Rensselaer Polytechnic Institute, and I completed the coursework for my PhD in Mechanical Engineering from the Massachusetts Institute of Technology. I am a member of the American Society of Mechanical Engineers, the Society of Automotive Engineers, and the Operations Research Society of America. Today's presentation will describe a revolutionary new concept in engine design: the Satz Rotary Positive Displacement Hot Gas Regenerative Engine, U.S. patent number 4,009,573. This presentation is based on my copyrighted book, Theory and Design of the New Rational Combustion Engine, and my paper, The Solution to the Gas Turbine Temperature Problem, published in Volume 20 of the International Journal of Energy Conversion and Management. The book, which was originally intended to be my doctoral thesis and is now available from Transpower Corporation, contains 28 engineering drawings, 30 tables, 800 equations, 17 figures, and excerpts from the 10 computer programs which went into designing this engine. Nearly 500 pages long, it is one of the most extensive studies of an engine ever written. I left MIT in order to secure patent rights on the new engine. As you can appreciate, I have a lot of material to cover and only an hour and a half in which to do it. Therefore, I ask for your strict attention. First, I will present an executive summary of the key points of the new design. Second, I will give a brief review of the gas turbine temperature problem. And third, I will present my proposed solution to this problem and explain in detail the new concept. Okay, first the executive summary. All previous Brayton cycle engines have utilized a separate compressor and expander, and thus have been limited in temperature on the expander side. To overcome this limitation, I have designed a new rotary positive displacement Brayton type engine in which each mechanism both compresses and expands the working fluid. Since each mechanism goes from cold to hot and back to cold, the material will remain at approximately the mean temperature of the compressed and expanded gas. Thus, much higher temperatures can be used with much less expensive materials. The mechanism is also unique in that the rotor is offset from the center of the stator so that the expansion volume is greater than the compression volume. Computer simulation indicates that the overall efficiency of the engine will be 57%. Weight will be 4.45 newtons per brake horsepower, which is 1 pound force per brake horsepower. And emissions of hydrocarbons and carbon monoxide lower than any proposed standard. The engine promises twice the fuel economy, half the maintenance, and 3/4 the first cost of the conventional Otto cycle engine. Okay, now I'll discuss the gas turbine temperature problem. The origin of the gas turbine temperature problem can be traced back to the very first Brayton engine, that invented in 1873 by George Brayton, a Bostonian. Compression took place in one cylinder and expansion in a larger second cylinder, a combustor separating the two. This first commercial heavy oil engine had an efficiency of 6.5%. The Brayton piston engine was in use a number of years before losing out to the Otto and diesel engines. I refer you to Appendix A of my book for a complete engine history chronology. Right now, I'll show you a transparency of a classification of all existing engines. There are two main types of engines, those which have fluid working media and those which have electron working media. I'm not going to go in great detail of these different types, but I'll just point out that fluid working media type engines are divided into heat engines and combustion engines. And the heat engines are divided into vacuum type engines and direct pressure engines. And direct pressure engines are divided into reciprocating type engines and turbine engines. Again, I refer you to the book for more details on this. I just want to stress that the first step of the project was a review of all existing types of engines. Okay, here's a continuation of the table, continuing with the combustion type engines. And here's the rest of this table, which lists the various types of engines that have electron working media. There are Q engines and E engines. And then, of course, we have various hybrids of these different types of engines. Now, this next transparency shows some of the history. Here's a time frame from 1600 to 2000 to the year, and I show here the steam engine, steam turbine, gas turbine, spark ignited engine, compression ignition engine, hot gas engine. And I give the main individuals involved in the development of these different types of engines here, together with the efficiencies that they obtained. The first working gas turbine was built in Paris in 1903 and showed an efficiency of 3%. Like the Brayton piston engine, there were a compressor and an expander, but these components were dynamic rather than positive displacement. It was not until a decade of 1950 to 1960 that the gas turbine was sufficiently developed to replace the reciprocating piston engine in aircraft. The main reason for this success of the gas turbine is its very high specific power density, the ratio of power output to weight. Also, it is a relatively simple engine running on an open cycle with constant pressure, continuous internal combustion. In addition, the Brayton cycle makes possible the use of a regenerator, which increases efficiency. Any engine which seeks to replace the gas turbine and other engines should have all of these advantages and more. The equation for the ideal thermal efficiency of the regenerative gas turbine is given in Ferri's thermodynamics as efficiency equals 1 minus T sub 1 divided by T sub 3 times the pressure ratio, that's expander pressure ratio, raised to the power K minus 1 divided by K, where K is the ratio of specific heats. T1 is the engine inlet temperature, T3 is the inlet products temperature to the turbine expander, R sub P, as I said, is the expander pressure ratio, and again, K is the ratio of specific heats of the working fluid. Note that as R sub P decreases to 1, the efficiency approaches that of the Carnot, Ericsson, or Stirling engines, but with no work done. With ambient air, there is not much that can be done with T sub 1 or K. The only parameter left is T sub 3, which is, again, the inlet products temperature to the turbine expander. So, with each increment of T sub 3, there is a corresponding increment in the efficiency of a gas turbine. Thus, the focus of gas turbine research over the past several decades has been to find turbine expander materials to withstand ever-increasing temperatures, the current limit being approximately 1311 K. One other method of increasing temperature has been to use transpiration cooling, in which water or air are circulated within the blading. If water is used, the heat absorbed would ordinarily be lost from the engine. If compressed air from the compressor is used, the heat could be recovered, that is, after cooling the blading, the air could be expanded in the expander. However, if the air does pass through the regenerator first, then not too great a reduction in blading temperature would be possible, for the blading would then be at some temperature between that of the combustion air and that of the cooling air. If the air does not pass through the regenerator before cooling the blading, then of course energy is not recovered. In addition to these heat transfer problems, there are practical ones. How can transpiration cooling be accomplished without drastically increasing the cost of the already expensive blading? Here then is the gas turbine temperature problem. There are no materials and presently no transpiration cooling methods that can be used to enable the gas turbine to run at such a temperature so as to be able to compete successfully against the Otto and diesel engines below 5,000 brake horsepower. Now, the next part of this paper will outline the solution to the problem. It will show how it is possible to use much higher temperatures while at the same time using much less expensive materials and with no transpiration cooling. Complete details of the new engine from advanced theory down to the design of the bolts and mounts is given in my book. Now, the solution to the gas turbine temperature problem that I'm about to present may appear obvious to the reader after it is stated. The fact remains, though, that the solution is original and unique, and as a result, the author was awarded a U.S. patent. All Brayton-type engines until now have had a separate compressor and a separate expander. This has been true both for Brayton positive displacement engines and Brayton turbine engines. What I propose is a new Brayton-type engine with each mechanism both compressing and expanding the working fluid. Thus, I propose that the compressor and expander not be separate. Some details of the new mechanism will be discussed in Section D of this paper. With the foregoing, we now have the solution to the gas turbine temperature problem. Since the mechanism goes from cold to hot and back to cold, the material will remain at approximately the mean temperature of the compressed and expanded gas. Thus, much higher temperatures can be used with much less expensive materials, and no transpiration cooling is needed. Of course, this principle is utilized in the conventional Otto cycle engine. The pistons of this engine are subject to extreme temperature, for example, 2800 K, but only momentarily. The variation in piston temperature is only about 15 K. This principle has never before been applied to a Brayton-type engine. To follow the Brayton cycle, the expansion volume of the engine must be greater than the compression volume. If the expansion and compression are to take place within one housing, the mechanism must be asymmetric. A search over the patent literature of almost 200 years reveals that heretofore there has not been invented a rotary mechanism of this kind. Again, the details will be deferred until later. The temperature limit of the present Brayton engine is the turbine wheel inlet temperature. The temperature limit of the new Brayton-type engine, which I naturally call the SATS engine, is that of the regenerator material. This can be shown as follows. Let T sub 4 and P sub 4 be the temperature and pressure of the fully expanded gas. Then, assuming adiabatic and isentropic expansion, T sub 4 equals T sub 3 times the ratio of P sub 4 divided by P sub 3 raised to the power K minus 1 divided by K. And after some algebraic manipulations there, we get that T sub 3 equals T sub 4 times R sub P raised to the K minus 1 divided by K power. Now that equation I just gave you can be substituted into equation 1 on the blackboard, and we then obtain the equation for the ideal efficiency of the SATS engine, 1 minus T1 over T4, where again T sub 1 is the ambient air temperature and T sub 4 is the temperature of the fully expanded gas before regeneration. Thus, the higher the temperature that the regenerator material can withstand, the greater the efficiency. For concreteness, let's compare the ideal efficiencies of the gas turbine and the SATS engine. Suppose that T sub 1 equals 302.6 K, which is, by the way, the SAE standard ambient temperature, and that T sub 3 for the gas turbine, that is the temperature of the inlet products to the turbine wheel, is 1311 K. Then by equation 1 there, we get that the efficiency of the gas turbine is 61.5%. That, of course, is the ideal efficiency, 61.5%. For the SATS engine, assume that the present maximum temperature that the regenerator can withstand is 1367 K. Thus, in equation 2, T4 equals 1367 K. And therefore, the efficiency of the SATS engine, that is, again, the ideal efficiency, is 77.9%. This is an improvement of 16.4 points over that of the gas turbine. It should by now be clear to the listener that the SATS engine should always be more efficient than the gas turbine. Any exotic new material allowing extra high turbine wheel inlet temperatures could, presumably, be used for the regenerator of the SATS engine, so the advantage should remain. Okay, now we'll go through a logical derivation of the new engine. The first step is to decide whether the cycle should be open or closed. Closed cycle engines using high-pressure steam, helium, or hydrogen are common in large power plants. However, the open cycle using air is more rational for the following reasons. A, air is free, whereas hydrogen, helium, or water is not. B, no storage of the working fluid is required. C, less complicated control systems may be utilized. And D, high-pressure hydrogen, helium, or water has the potential for leakage and explosions. So the new rational engine will utilize the open cycle. The next question is external or internal combustion. With an open cycle, combustion can take place internally or externally. Internal combustion is more rational because A, it eliminates the need for a heat exchanger between the combustion gases and the working fluid. And B, it allows cycle temperatures about 1600 K above that used in external combustion. In internal combustion, the containing walls can be cooled from the outside, which contrasts with the external combustion, the containing walls of which must transmit the heat from the combustion gases to the working fluid. Higher cycle temperatures, of course, give higher cycle efficiencies, the magnitude depending on the thermal cycle employed. The new rational engine will have internal combustion. Step 3 is constant volume or constant pressure combustion. Internal combustion can take place at constant volume, at constant pressure, or at some combination of the two. Constant pressure combustion is the most rational because no sudden pressure rise occurs in the cycle, thus reducing the potential for leakage. Lower cycle pressures are used, thus allowing lighter containing structures. The pressure in a constant volume process might reach 7,000 kilonewtons per meter squared, whereas the maximum pressure in a constant pressure cycle might only be 700 kilonewtons per meter squared. Considerably fewer pollutants result after constant pressure combustion as compared with constant volume combustion. For example, gas turbine or Stirling cycle engine may have 5% of the hydrocarbons in carbon monoxide and 50% of the NOx of an uncontrolled Otto cycle engine. And many different kinds of fuels may be used: kerosene, diesel fuel, jet fuels, gas, gasoline, etc. So the new rational engine will have constant pressure combustion. Okay, this way. Okay, the next step is 4, intermittent or continuous combustion. Constant pressure internal combustion can take place intermittently or continuously. Continuous combustion is more rational because A, it eliminates the need for costly fuel metering and fuel injection equipment, and B, it results in much more smooth engine running. The new rational engine will have continuous combustion. Step 5, reciprocating or rotary mechanism. The four main disadvantages of the reciprocating engine are: A, many parts are required to change reciprocating motion to rotary motion, and the parts are difficult to balance. B, parts have to be heavy and strong to counteract the large inertial forces created by the change in direction of the pistons. C, near top and bottom centers, very little of the energy arising from the combustion process is transmitted to the crankshaft. For example, at a crank angle between 155 degrees and 180 degrees, and between 0 degrees and 10 degrees, less than 26% of the energy might be transmitted. And D, usually valves and camshafts are required to open and close engine intake and exhaust ports. In contrast, a rotary mechanism is simple, small, light, and smooth. Very simple shafting can be used. The new rational engine will be rotary. Step 6, compression expansion accomplished by separate mechanisms or the same mechanism. A rotary engine may have compression and expansion taking place in separate housings or in different areas of the same housing. As I have stressed, it is more rational to have compression and expansion taking place within the same housing so that the mechanism goes from cold to hot and back to cold, thus making possible very high cycle temperatures while using relatively inexpensive materials for the mechanism. The Wankel rotary engine has compression and expansion taking place within the same housing and can thus use temperatures up to 2800 K. This contrasts with the gas turbine, which is currently limited to temperatures of 1311 K. So the mechanism of the new rational engine will serve as both compressor and expander. Step 7, incomplete or nearly complete expansion. The working fluid can be expanded completely or incompletely. Complete expansion is much more thermally efficient than incomplete expansion. For example, for the same compression ratio, the efficiency of the Atkinson cycle, which is a type of complete expansion Otto cycle, is 10 points higher than that of the Otto cycle itself. However, engine size, mechanical friction, fluid friction, and heat transfer are increased with more expansion. The optimum amount of expansion is reached when the increase in thermal efficiency is just balanced by the mechanical losses. In any case, though, the expansion volume should be greater than the intake volume. This rules out all previously existing rotary positive displacement engines with compression and expansion taking place within the same housing because they are all symmetric. The new rational engine will have nearly complete expansion. Step 8, liquid or gas film lubrication. Engine parts may be lubricated by a gas film, a liquid film, or a solid film. Where it can be used, the gas film is the most rational. It produces the least friction while avoiding high cost and complication. Where gas film lubrication is not feasible, solid film lubrication is the next most desirable. High-temperature durable coatings of calcium fluoride are now available. Oil or synthetic oil lubrication is the least desirable. Complicated arrangements must be made to supply the oil, and some of it is bound to get burned and used up. The new rational engine will use gas film and solid film lubrication. Step 9, air or liquid cooling. Engine cooling can be accomplished by the air, by liquid coolant, or by the fuel. In both air and water cooling, energy is simply dissipated directly or indirectly to the atmosphere. In fuel cooling, engine heat goes to the fuel before it is burned, thus conserving part of the heat that would normally be wasted. This principle of regenerative cooling is often used in liquid propellant rockets. Besides, it is desirable to preheat kerosene before burning it. So the new rational engine will have regenerative fuel cooling. this up. Okay, step 10, low, high, or medium speed. Very large diesel engines run at 100 RPM. Very small gas turbines run at 60,000 RPM. The lower the speed, the lower is the power to size ratio and the more heat transfer out, but the lower the fluid friction. The higher the speed, the better the power to size ratio and the less heat transfer out per cycle, but the greater the fluid friction. The new rational engine will have a medium-high speed, approximately 12,000 RPM maximum, to have a good power to size ratio and low heat transfer losses without undue fluid friction. Step 11, control by fuel, air, or both. Engines can be controlled by throttling the air, by metering the fuel, or by both throttling the air and metering the fuel, or by changing the compression ratio. The latter has so far proven impractical, but should be considered a remote possibility. Control by changing the air-fuel ratio, such as in gas turbines, diesel engines, or stratified charge auto engines, is efficient only over a limited range of speeds and loads. For a broad range of speeds and loads, control by throttling the air and metering the fuel so as to keep the same fuel-air ratio appears to be the most rational, providing fair part-load performance, except close to idling where pumping losses are large. In addition, by varying both air and fuel, excellent responsiveness is assured. The new rational engine will be controlled by varying the quantity of air and fuel while keeping their proportions the same, the ratio being that required for proper engine temperature and minimization of pollution. For transportation vehicles, the optimum configuration would consist of two mechanisms. One mechanism might be powered for city driving, both for highway driving. In this manner, better part-load performance can be obtained. And step 12. Non-utilization or utilization of exhaust heat. Almost a third of the energy supplied to an Otto cycle engine leaves the exhaust pipe unused. By changing the thermal cycle so as to be able to use a regenerator, much of the exhaust heat can be put back into the cycle. In this manner, the exhaust can come out relatively cool, about 560 K, eliminating costly materials for the exhaust ducts. The new rational engine will have a regenerator. So, with all these parameters, we get the SATS rotary positive displacement hot gas regenerative engine. Now this next table shows the rational and irrational qualities of existing engines based on the derivation I just gave. I'm not going to go through each of these, but I have on the chart the Otto engine, the Wankel, stratified charge, diesel, Rankine, Stirling, and gas turbine. And I go through each of the steps that I just presented, with a plus indicating that that cycle or engine has that feature, and a minus if it does not. Now, section A of this paper compared the SATS engine with the gas turbine. What about other thermal cycles? As the listener or viewer knows, the ideal cycle efficiency of the Otto cycle engine is given by this equation. 1 minus 1 divided by R1, which is the compression ratio, raised to the power K minus 1, where K, as usual, is the ratio of specific heats. In order to obtain an ideal efficiency of 77.9